Okay, 2-5 day 2. It's happening right now. There's nothing you can do to stop it. Oh wait, you could just hit the pause button, or you could turn it off, but don't do that. 2-5 day 2. We're still talking transformations. We'll kind of see three things today. One, I'll show you what we call non-rigid transformations. Okay. Now, by the way, just to write by that definition. If you go back to the list of 3 types of transformations that I gave you, this is the one that we call a stretch. Okay. It changes the basic shape of the graph. Okay. We'll talk more about that. But we'll talk non-rigid transformations. Second thing on the next slide is I'll take you through multiple transformations at once. Okay, and then I'll give you a little summary that kind of explain, is just a good little, we'll talk through it through a little bit, but just kind of has all the transformations together. Okay, here's g of x. All right, let's get into non-rigid. The way I like to describe it is stretched vertically by 3. Now, a good little key word. It's not technically like, real mathy type term. But is a really good way to think about it is that the graph is going to get skinnier. Okay, this graph is going to increase 3 times as fast. Okay, so now to be clear, when we say it's going to change the shape, because we're still working with absolute value, right? Again, absolute value graphs are just nice graphs to look at transformations on. It's not going to change it from being a V shape. That's still going to stay the same, but could it be a wider V or is it going to be a skinnier V? And the 3x will make it skinnier. Okay? Whereas this one, we'll do a table for both of them. That one we'd say is stretched horizontally by 3, and it gets wider, okay? The difference here being, okay, we call that number typically A. Out here we have a case where A is greater than 1, and then over in our second one, in this case, A is between 0 and 1, okay? That's the kind of thing that's going to come on the last slide is like, oh, hey, here's how we summarize all that, okay? Is it stretched vertically or horizontally? Okay. I'm going to make a table for each one. Now the graph hasn't been moved side to side, so I'm in good shape to just center this at 0. Those 5 values will work pretty well. Basically with showing you one of them here. If I put in -2, here's what's going to happen. Put that in for x. Take the absolute value, and it's 2, and then it gets multiplied by 3. So my y value ends up being 6. Okay. If you wanted to pause here and go and fill the rest of the table in on your own, certainly could. If not, you can proceed with me. And you can just take my word for it that that's how the rest of the table comes out. And we're looking at this. Tip of the V is going to be in the same spot. Again, if you think about the other transformations we looked at, that makes sense. Okay? There's no shifts. This graph did not move side to side. It did not move up and down, so it's still centered right at 0, 0. And then I've got 1, 3, 2, and 6. Actually, it takes me a little bit up off the graph. -1, 3, -2, 6. I should throw some labels on here. That's graph G. And of course, our original was just a non-transformed absolute value graph, which we call the parent function, remember? And that's what we mean by skinnier, right? Taller and skinnier. It was stretched vertically by 3. For each x value, the y value is going up 3 times as fast. Let's do another one and take a look at h. Here, and we do the absolute value and then just divide it by 3. So we end up with some fractions here. Still centered at 0, 0. As I go over to 1, I only go up a third. As I go to 2, I only go up 2/3. So the right side would look something like that. Same thing over here, 1/3. Should be a little bit higher. Oops. Right there. And there's h. Okay. Still has that V shape, right? Again, when we say, it can, non-rigid changes the shape. We're not talking like Maui from Moana. It's not like a shapeshifter, like, switch the graph into anything you want. The same basic structure is going to be there, right? But the width of that V shape of the absolute value graph, this particular transformation will mess with that. It'll make it wider or skinnier. But not like Maui. We're not talking shapeshifters. Totally different thing if you were getting those two confused. Absolute value graph and transformations. Demigods that can shapeshift, not the same. Okay. All right, we'll make a table with this one. By the way, I'm going to get my graph labeled again. There's my parent function, just the absolute value of x, which we'll call f. All right. I had mentioned yesterday that I'm leaning towards like test-wise 3 transformations. Now I put some familiar ones on here that we've seen in the last couple of lessons. This one should jump right out at you. We just saw it. Okay, so vertical stretch by 3, right? Again. Sorry, I had to check one thing. One thing on that previous slide to make sure I got it in there, and I did. Okay, you got a vertical stretch. Okay, these other two involve addition and subtraction, so now we're talking shifts. These were the rigid transformations, right? The 3 will make it skinnier. These other 2 will just move it, okay? Shifted 1 unit left. Shifted 2 units down, okay? And you look at that function, which we're calling function k, and it kind of looks a little bit more like some of the functions we're accustomed to seeing, right? A lot of the graphs we create and the functions we do word problems with, they have like 3 transformations going on. Just because, especially if it's a word problem, there's some real life data the problem is about, and we want the function that fits the data. So we use whatever transformations are needed to fit the situation, okay? There's no context to this problem, but nonetheless, it's got 3 transformations. Make a table. I'm going to have specific points, right? Because here's the deal. if I wanted to just like sketch it off the transformations, I could do a pretty basic sketch, right? I could take the transformations and say, okay, 1 to the left, 2 down. Okay, so it's going to be like right there. And then this V shape just needs to be, you know, distinctly skinnier than the parent function. That's a pretty bad sketch. But honestly, in terms of like ballpark of what we're looking at, it's not that bad, right? That's what I'm expecting this, as I'm just kind of thinking through the transformations, because I am going to do a table that has exact solution points. Okay, I'm going to find 5 of them. But it's not bad to think in more general terms about the transformations. What is my final product going to look like, right? A little bit to the left, a little bit down, a skinnier V that still opens up is what we're looking at, okay? Now I'm going to use this to my advantage here. 1, 1, 2, right at the base of that V. Excuse me, -1, -2. That's definitely where I want my table centered, okay? That you could also really see from here. If you get a horizontal shift, typically wherever it was shifted to, that's a good X value to put smack dab in the middle of your table. It's not like a perfect guideline, but it's a pretty good one. It'll usually work very well. Okay. Now just to kind of show you one, I'm crunching some of the numbers here. We have 3. I have to take the absolute value of -3 plus 1 minus 2. Okay. There's 4. Okay, so when I plugged in -3, I got 4. Okay, I got 3 others. I'm not going to, I mean, the number crunching would look the same. I don't really have the space here, nor do I want to write them all out. But if you plugged in -2, okay, this is another point. If you want to just do the work yourself and verify, good point to pause. Or you can certainly feel free to double check my work. I got 1, 1, and I got 4. Okay? All right, so I go 3 to the left, 1, 2, 3, 4 up. That point is going to be on my graph. -2, whoops, that's not the right point. That's 2 up, not 4 up from where I was, 4 up from the x-axis. Oh, and I can't find my eraser. This problem is going terrible. It's going terribly wrong. That's okay. That's better. Should go right there. All right, -2, 1. Zero, 1. And then 1, 4, right? You can start to see the outline of it. Try to make these lines as straight as I can. Not perfect. It's okay though, it's just a handwritten sketch. And there's K, and you know, it's a little more accurate because I plotted some exact points, but that little basic sketch I made a few minutes ago, not too bad, right? A little bit to the left, 2 units, a little bit down, opens up, got skinnier, okay? Good example to study off of. The only thing you didn't see there is a reflection. Could I have thrown in a reflection and made a 4th transformation? Yeah, that'd be worst case. I'll look through some of your assessments, and I might give you a hint as we get closer to checkpoint and test time, like, are we going to take on 4 transformations? Maybe. We'll see. I for sure, I mean, this is a good one to study off of for now. I expect you to handle 3, without a doubt. We'll see about 4. All right, here's the big table that I was talking about before. Here's one thing I want you to do, okay? These last 2 down here, the horizontal compressions, that part, cross it out. Those are not common, okay? Because here's the deal. Go up here where it says, we talked about this case, right? Because basically the two that we saw today are right here, a vertical stretch and a vertical compression. If you want to take a vertical compression and you want to call it a horizontal stretch, you can. They're the same thing, right? In fact, if you relate it back to that first example that we did, this case right here where A is between 0 and 1, that's the case where it got wider, where it was bigger. For a vertical stretch, I would really say one thing to adjust here. Greater than 1 is really what it should say. The absolute value is greater than 1. If you want to take the approach with the wider, skinnier, right? We can think about it in those terms. When that value that we're multiplying by is out front, right? If it's bigger than 1, we could say it's getting skinnier. If it's between 0 and 1, it's going to get wider. Now, I probably shouldn't have crossed this out because you could have a case where you see a function and, okay, so let's do this. I'll bring this back. We're not going to cross it out. Sorry if you did. Well, I suppose you probably didn't write down the whole thing. So let's not cross it out. Just know that these two down here I'm just going to give you the note. They're not very common. Right? I wouldn't have the expectation that the whole like b over x. Just notice it does the opposite, right? If you're dealing with the x variable, the division would, if it's between 0 and 1, it would stretch it vertically, and if it's greater than 1, it would compress it, okay? Don't expect to see those a ton. Really, the A situation, because again, you could mess with A. If you want to stretch the graph and make it wider, you can do that with A. You don't have to have this, there's not this need for the value of B to do it that way, okay? All right, that's a good look at your rules. By the way, the rest of this, from here on down was day 2, right? The reflections and the shifts, that was all day 1. Okay, so we covered all those. All right, let's call it quits there. A little preview of 2.6, right? Function operations, which we've done a little bit of: addition, subtraction, multiplication, division, and that little function composition we talked about. Where you plug a function into another function, that's coming in 2.6.